Welcome to a presentation brought to you by the American Wood Council. Thank you for your participation in our webinar today. This webinar is intended to provide general information only and does not constitute professional or engineering advice. Please note that this webinar is being recorded, and by remaining a participant, you automatically consent to such recordings. If you do not consent to being recorded, please disconnect from the session. This presentation is worth 1.5 LU HSW with the AIA and 0.15 credits with the ICC. To receive credit for the course, you must attend this webinar for a minimum of 80 minutes. At the end of 80 minutes, you will see your certificate appear on your webinar console. Your certificate will also be uploaded into your learner profile on learn.awc.org, provided you registered for today's webinar with the same email address as your account profile. At the end of today's session, our presenter will have a live Q&A with the audience. Please input your questions into the Q&A panel throughout the session. And now for today's presentation.
Well, good morning, good afternoon, and good evening, depending on where you're located. Welcome to the webinar, the overview of the AWC Fire Design Specification for Wood Construction, the 2024 edition. My name is Paul Armstrong. I will be going through this particular presentation with you. I am the Western Regional Manager for the American Wood Council here, and I'm based in Southern California. If you should have any needs, feel free. At the end of all things here, the very last slide, I'll give you some contact information, and feel free to reach out. And I can help you with certainly any questions related to the FDS, or at least get you to the people who can answer things. Or if you have questions on other areas of certainly of note in wood construction, please feel free to reach out. You can email me any time of the day or night, weekends, that kind of a thing. I try to get to them as soon as I can, and then try to find the best solution or a response for whatever question you're having. Obviously, as I said before, today is an overview of the Fire Design Specification. I'll be using the acronym as it shows on the slide, FDS. It's a whole lot easier to use that than to say the whole title. This particular standard is new, if you will, in terms of its reference within the 2024 International Building Code. So we're very excited about having this particular standard available. We're in full support of this, and it has made its way certainly through most of the code change proposals to include it within the various reference areas of the International Building Code that we'll be talking about today. So the course description, as I said, is we're going to talk about the FDS. It is related to wood construction. It's not intended to apply necessarily or even at all to other construction materials. This was developed by the wood industry for use in wood construction. And we will be talking a little bit, certainly, about the history of this particular standard. We're going to go into some of the existing wood provisions. We don't have a lot of time, unfortunately, to do that. But we'll talk a little bit about what the building code has had in reference to what the FDS has within its covers. And then certainly we'll be talking about some of the new information, as you can see at the bottom of this slide, related to how we calculate the fire protection or fire resistance of protected wood construction, or even, for that matter, exposed wood elements. So we'll be going through some of that. I have a tendency to address issues from an enforcement standpoint. That is my background. I started with the City of Los Angeles many years ago, Department of Building and Safety, and then went from there to actually the model code groups. I went to the International Conference of Building Officials, which some of you may remember. It's one of the legacy model code organizations, but then made it the transition to the International Code Council. And I did that for 14 years in the code development process. If you ever have the opportunity to work with them, it is a great experience. It's very satisfying. And, you know, there are a lot of great people across the country and frankly, even internationally in our business that are just awesome to work with. So I'd highly recommend that as well. I went from the model code organizations back out into more of the private consulting side, of the business, and have been building official of a number of jurisdictions, and have had the opportunity to enforce the codes on all kinds of different projects, especially obviously wood construction. And so looking forward to going through this with you today. As I mentioned, we're going to talk a little bit about the history of this criteria that is found in the FDS. Back in 1977, which doesn't seem all that long ago right now, T.T. Lee actually developed and published an empirical method for calculating, if you will, heavy timber beam and column fire protection. It was a good first attempt at it. It was really good, actually. It estimated a reasonable time frame for the fire resistance, and was ultimately adopted by the National Building Code of Canada. Well, in 1984, the predecessor organization to the American Wood Council is the National Forest Products Association, yes, NFPA. They were successful in getting this particular method adopted into the 3 model building codes that were published at that time frame. And so the research continued, and there were several reports that were issued by the research team at the Forest Products Lab and all of that. And in 1988, Dr. Ed King and Robert Glowinski, still with the National Forest Products Association, published an article in the Forest Products Journal entitled "A Rationalized Method for Calculating the Fire Endurance of Wood Beams." While its ability to predict the performance of wood beams was mixed, it was the first attempt to really develop a fully mechanics-based method that estimated the contribution of the elevated temperature region ahead of the char front. So continuing on in the same year, there was really a breakthrough in the understanding of what they were doing. And Dr. White issued or released his thesis on charring rates of different wood species. Now, that particular thesis was actually very, very complicated, and it took several years for our AWC engineers to really understand what he had discovered. The point, really, at which wood burns fastest is just after ignition due to the presence, obviously, of oxygen. It has the source, there's an ignition, and then oxygen is part of the group that actually causes fire to occur. So as the char layer forms, available oxygen for inside where the actual wood is, that is protected by the char layer, becomes greatly reduced. So the wood continues to undergo pyrolysis, but at a decreasing rate then. So then the protection is being provided by the charring of the wood on the outside, and it's protecting that structural core then of whatever wood element you're looking at. So Dr. White provided various equations that he fit for the various species he tested. And the best fit really was a nonlinear char model. AWC engineers really discovered that all species altogether, had a similar nonlinear relationship in this regard. So even though there were small differences between various species, it was found that a general equation could be developed, and was developed, for all species. So through the mid-90s, AWC engineers worked on this new mechanics-based model combined with this general equation that was based on Dr. White's work, and with his assistance, comparisons were made against full-scale test results of the beams and columns that were tested. Moving on along down that line, obviously there was more research being done at the end of the 90s. In 1999, AWC published the first version of Technical Report number 10. And that report is entitled Calculating the Fire Resistance of Exposed Wooden Members. This first version of the technical report, as it's known now, TR10, primarily focused on comparing AWC's new mechanics-based nonlinear char model with what was done back in '77, T.T. Lee's empirical method. And in every case, TR10 model fit the test results better, and it allowed for the design of beams and columns using all of the structural design provisions from the National Design Specification, which AWC publishes as well, including various loading configurations, the effective bracing, and beam column interactions. It also allowed the mechanics to be extended to 2-hour fire resistance from the original 1-hour fire resistance limitation. So this first version also then took a step out away from beams and columns and started to address heavy timber decking at the same time. So in 2002, the design provisions that resulted from all of this work were adopted into the NDS in Chapter 16. As part of that, provisions were immediately then available to designers, engineers, and the like, since it related to fire design rather than structural design. So the challenge we had is that we had just mixed fire design in with a structural design standard, and there was still some confusion then about the criteria's applicability. In 2003 then, we had a reference to the NDS Chapter 16 in the International Building Code Chapter 7, which covers all things related to fire and smoke protection features for the fire design of structural wood members. And so for the very first time, this new criteria, this new model was included as a reference standard in a model building code. Also in 2003, the American Wood Council released a new version of TR10, which included the analysis of large tension members tested at the Fire Products Lab as well. So recognition of this criteria started to increase through, if you will, the reference to NDS Chapter 16 and TR10. In fact, one of the first reported cases of its use in fire design was for a large timber roof truss assembly that was utilizing U.S. glulams in Taiwan. Very, very interesting to see all that go on. So work, as I said, continued on TR10. The American Wood Council engineers continued to do their research and study of the work that had been done. And in 2013, the mechanics-based nonlinear char model was used to predict the results of unprotected floor joist assemblies. Okay, as a result, this of the model's ability to predict the performance of these assemblies themselves, it has been used then as the basis for having these assemblies be considered as membrane protected provisions or assemblies for wood engineered I-joists. So the limitation that was originally applied to only allow for the use of large cross-section wood members was removed from the previous, if you will, from the standards that referred to this in TR10 and Chapter 16 of the NDS. So in 2015, this model was used to accurately predict the fire test results of structural composite lumber, beams and columns, and all kinds of other types of engineered wood products, including the development of a new model for exposed cross-laminated timber, CLT. This is very important today because this is the product that is used, at least recognized mostly, as being part of the mass timber movement that's going on out in the industry these days. So the char model that was developed for CLT really was the first deviation from the original nonlinear char model. And it uses the same kind of char model, but resets itself as the char front actually reaches the glue line between each layer, if you will, within the CLT assembly. So again, continuing on along, as I said, they were used to actually provide us with information on how to apply this criteria to engineered products. So the next big step was in between 2015, and the engineers there at AWC spent a lot of time really going over this and developing this, because all prior modeling had assumed that the fire resistance of wood members was inherent in the behavior of wood. So as work began on the tall wood building initiative, okay, heading towards our mass timber criteria, it became very clear that added provisions for the contribution of the protection needed to be addressed. And as a result, AWC and industry engineers pored over this information for wood structural members and, of course, for assemblies that are protected with wood cover of different types, fire-rated gypsum panels, things of that nature, and even insulation. Both protected large members, beams and columns, obviously, and wood assemblies, stud walls and floor assemblies, and maybe even roof assemblies. All of those were analyzed. With the development of these new provision or new protection options, AWC realized that design provisions need not be limited to structural fire resistance time, but could be expanded again to predict thermal separation from one side of an assembly to the other and burn through. And we're going to talk about those here in just a little bit. Two additional then requirements for assemblies were added that were added to the fire separation requirements between occupied areas then. So in 2018, guess what? Another version of TR10 was released. It had the expanded scope built into it, and the title itself became much more expanded or inclusive by saying the title is Calculating the Fire Resistance of Wood Members and Assemblies. And that included the design of all protected wood members and assemblies at that time. So we're getting closer to today, 2020. Another version of TR10 was released. And this, in some ways, to me, in just coming up through the business, is one of the bigger jumps that they built into TR10, is that they added connection design examples using the provisions of TR10. In other words, you can provide protection for the connections. We're going to talk about this here in a little bit in wood construction using exposed wood members then again, of special interest, obviously, were examples on how to design, if you will, the protection required for our new types of construction, new type 4A, 4B, and 4C construction, which are mass timber as well. So as the scope and all of that, the demands, if you will, on TR10 expanded, there was an issue. Okay. And that was including all of this fire design criteria, in other words, non-structural design criteria into a structural design standard, the NDS. That standard could be considered to be out of scope. So here we go. The AWC engineers then drafted up the first edition, which resulted in a pre-release release, as you can see, in 2021 of the FDS. And the first real standard that was developed, if you will, the real fire design specification for wood construction standard was the 2022 edition. Now, and of course, we don't show this on the slide here, but then we've also reorganized. We built in some clarifications, some good information that are found in the 2024 edition as well. So that's just kind of a run through of the history, obviously from 1977 until today. And we have now the FDS in front of us. So the FDS itself, we are going to start like we always do at the beginning of the standard and work our way to the end. We're good engineers. We like to have that kind of process. It's simple. It's predictable. We can understand it. Okay. A lot of what we're going to talk about today in the FDS is really already found, in part at least, in the various model codes that are out there, the International Building Code in particular. Okay, so we have really 3 chapters and some appendix chapters. We're going to talk about them here in just a little bit. Again, this is a overview of the FDS. If you have any questions related to the criteria that is found in the FDS or that we talk about here today, please feel free to reach out. I don't know everything. Nobody does, but our AWC engineering staff, they know an awful lot about this. So we can get you the information as you need. So just as a general, if you will, outline of the FDS Chapter 1 itself, you can see general requirements for fire design, like in every model code and every other standard out there. We start with this kind of general criteria. So we start off with a general statement, includes a scope, things of that nature. Then, of course, we move into the terminology. And we're going to talk about some of the terms, 3 of the terms here today. And I've already given you a heads up on those particular terms themselves. And we'll go through them in a little more detail. But it's something that is going to be new for our enforcement community out there. And it's probably new for a lot of the design community too, that have been using the International Building Code or other types of codes that are out there. We just have a little different way of looking at things. Maybe it's a little more specific. That's a better way of looking at it. But the terminology, these are our definitions. This is the language we speak. It's how we communicate in this particular business. Certainly in this case, in terms of the fire design of wood elements and assemblies. So then we go on. Obviously, we need to explain notations. We need to explain the standards that are referred to or used, if you will, in this particular document. We're going to talk about and go through some of the tables related to, what makes members heavy timber and show you what that is in the FDS. And you're going to find, I think, that it looks very familiar, although there's more information in this particular document than in the model codes. Combustibility requirements, and then obviously the fire resistance rating of construction itself are addressed in this particular chapter too. So a lot of this is going to be very familiar for us, but we're going to go through some of these here in just a little more detail. So the first one, obviously, I already talked about this particular term, and we got 2 others we're going to talk about that relate to, if you will, the testing or certainly the calculation methods that are found within this particular fire design standard. So burn through time, it's just as the definition says, this is the time that it takes for flame to pass through an assembly. Okay, it is not applied to the protection of wood members themselves like beams and columns, because we're not really calculating, if you will, the passage of flame through that assembly. What we're doing in that particular case when we're providing that kind of fire protection is we're trying to protect the structural integrity of that element itself. And so we have another term that we apply to that. This one, as you can see, it's a period of time before burn through occurs. We get that during, go figure, ASTM E119 fire resistance test. That is the icon, the standard that we use for so many rated fire resistance rated assemblies. Okay, or as determined by the design methods in Chapter 3. We will go through that. That's Chapter 3 in this particular standard. Second term, structural fire resistance time. It's that period of time a material, member, or assembly performs its structural function during one of these tests, ASTM E119, or we expand the application to a UL standard, very similar test, obviously for testing the fire resistance rating of various elements. Okay, we want to make sure that what we're providing in terms of the protection protects the structural capacity of whatever element we're looking at the time. Okay, whether it's a beam, whether it's a column or an assembly, we want to make sure that it performs certainly for the length of time that it's intended to perform. So that's in here as well. A lot of us that are used to the model building codes, frankly, are used to this particular term without even knowing that, because that's exactly what we had as an evaluation in the building code per se. Now, the interesting thing about it is that the standards that are referred to here actually build in the burn through, if you will, methodology, as well as the thermal separation time during the tests themselves. So again, thermal separation time is when you have an assembly, okay, and you're trying to prevent fire from moving from one side of a wall to the other side of the wall, either as the passage or the products of combustion, or the rise of temperature on the opposite side that could cause combustible materials to spontaneously combust and then defeat the purpose of the wall. Okay, so we had that already. We just didn't call it out as a defined term in the past. And you can see that this reference standards, again, are ASTM E119 or the ANSI UL 263 fire resistance test. And then, of course, we have a reference at the end of this, as we do with all three of these terms, to the design methods found in Chapter 3. We'll get into that here in just a minute. Section 1.5, we moved away from the definitions. We're not going to talk about certainly the standards that are imposed. We can go through that after, if you will, offline. Email me, that'd be fine. If some of you have my cell number, I can give that, in my email, obviously. Feel free, we can talk about any and all things related to this. But in this particular case, we're going to chat about what actually defines a wood member as a heavy timber member. And you can see that we have a much larger table now than we had in the building code related to certainly roof framing members, floor framing. You can see that in the table, columns, decks of various types, exterior walls and interior walls. Okay. These are the minimums, if you will, the minimum sizes that heavy timber elements need to be to, if you will, gain the benefit of having that particular classification. Okay. One thing that is really new is we've had some questions on this too over the years. And even back in the day when I was taking questions when I worked at the model code organizations, what do you do for toppings on heavy timber floor decks? Well, you can see, and unfortunately it's a pretty small table there, table 1.5.3. We have a number of different materials and then the minimum sizes that are attributed to be considered to be a part of a heavy timber assembly. So we have all that now. We have more information that can be used for the classification of heavy timber elements or members, assemblies, things of that nature. And it's giving us certainly a better idea of what really makes up heavy timber construction. So then obviously, we're getting towards the end of Chapter 1. We're going to talk about our fire resistance rated members and assemblies. Okay, and again, this is for wood construction, obviously. The whole standard is based on wood construction only. So the criteria itself goes through for wood members and assemblies, and it talks about certainly, like we would expect, the continuity of the fire resistance rating, if you will, the continuity of the material that's providing the protection for these members and assemblies. When you have supporting elements for these fire resistive assemblies, what do you have to do with those? Do you have to protect them in any sort of manner to the same degree as maybe a horizontal floor assembly, or can it be reduced, that sort of thing? All that's described in here. We have the design of fire resistance rated wood columns and beams that are found within various assemblies, such as wall assemblies or floor ceiling, roof ceiling assemblies. In other words, the membranes of those wall assemblies, floor ceiling, and roof ceiling assemblies are providing the protection, fire resistance protection of those particular elements that are found within those assemblies themselves. We also talk about the fire resistance rating design of multi-span beams. We haven't had that in the building code before, so there's more criteria related to that too. And then, as I said before, one of the most interesting things to me in this particular standard is the design of the structural connections themselves of these fire resistance rated assemblies to either other fire resistance rated assemblies or maybe, perhaps if it's allowed, non-fire resistance rated assemblies. And we can provide protection, and we'll show you just a brief detail related to that at the end or towards the end of our presentation today. Another thing that we talk about in this particular section is when we have an intersection. Okay, when we have joints, when we need to provide protection there because the wood assembly, if you will, doesn't either pass through and provide the protection, or there's an intersection between various assemblies and all that. We're very concerned in these cases of having fire burn through that intersection, that joint, if you will, and then obviously defeat the purpose of the fire resistance rating assembly that is being provided. Okay. We have requirements like we have in the building code for fire resistance resistant joint systems. Okay, industry's been very involved in that, and that's built into this particular standard. And then just like we have with joints, the protection of membrane edges in various types of assemblies, including the very specific detailing of gypsum panel wall to ceiling intersections or wall-to-wall intersections, and how we have to do that so that we don't provide, if you will, a straight path through that intersection to potentially the inside of the assembly or the other side of that entire wall or floor ceiling assembly itself. Okay, very, very interesting to see this. This is an area we're going to talk about this just briefly towards the end of the presentation and give you some recommendations when you're doing a plan review and somebody's intending to use this particular standard. Okay. All right, that was chapter 1. Moving on, we have chapter 2, and it's going to talk a lot about some things that we're very familiar with that are in the building code, if you will, scattered in the building code. And like a lot of chapters, we have to start with the scope of the chapter itself. But the ignition resistance and flammability, excuse me, of wood products is addressed here. It could be, again, very useful, this particular section, for limited, if you will, combustibility or limited ignition or flammability types of concerns or products to look at, if you will, those products with this in mind. Okay. Then we're going to go on to flame spread performance. Obviously, we're very used to dealing with flame spread types of analysis. We'll get into that here in just a little bit. And then the vertical and lateral flame propagation, that is the ability or hopefully lack of ability of a flame front to move either vertically or horizontally on, these different elements and assemblies, and try to limit that so that it doesn't get to areas that are maybe weak points or openings that need to be protected, and to protect those too. And then when we get to 2.5, again, this has been around for a long, long time, our fire stopping, our fire blocking, and draft stopping criteria. You're going to see certainly the protection of penetrations addressed here, like we've had in the building code for a number of years. And then certainly within wood assemblies, the fire blocking and typically vertical assemblies, and the draft stopping in typically horizontal assemblies that is called out. So moving on into that, ignition resistance. Okay, we have, again, a standard that is applied, obviously NFPA 268. It's already in the building code. We are in terms of working with wood construction, we find that wood products are typically exempt from the current NFPA 268 test because ignition usually occurs either at, you can see the incident radiant heat flux, either at or above the heat flux of 12.5 kW per meter squared. But as a result, in the codes themselves, wood products are typically limited for their use as exterior coverings because they are combustible, and we get that. Okay, there's a lot of work going on with this. You can see well, it's a little bit of a fuzzy picture of the test apparatus at Southwest Research Institute and all of that. It's kind of interesting if you ever get the opportunity to actually go and view tests. And I would hope that some of our ICC chapters, if they have any testing labs in close proximity to their members, it wouldn't be a bad idea to have a field trip to see how the testing of whatever construction material occurs in these particular configurations. So flame spread, we get that. We've been dealing with that for a long time. Okay, you can see that the flame spread classifications are exactly what we have in the building code: Class A, Class B, Class C. You can see the ranges. Class A, if you don't know, is our most restrictive or provides the most protection, because it really limits the movement of flames along vertical and horizontal types of applications. Okay, we see Class A flame spread applied, as you can see in the table below. In this case, it's flame spread requirement for business and a store or mercantile types of occupancies. Class A is for non-sprinklered exit stairways. Okay. And then there's a benefit for having sprinklers. Obviously, in that particular row, you can see it backs down, if you will. One classification gives a little more flexibility in terms of the products that can be used. The reason being for that is that and it's a completely different topic, but our means of egress criteria found in Chapter 10 of the International Building Code, it does have travel distance limitations within different areas of a building, different interior areas of a building. However, when you reach an exit stairway, that travel distance stops. That is an exit element. That travel distance then, since it has stopped, the determination has stopped, is unlimited. And so when we are putting occupants in a situation where they could be within an enclosed interior environment for an unknown amount of time, we're going to provide them with as much protection as possible. Okay, that's why in non-sprinklered conditions, and that's the entire building is provided with this kind of a automatic fire sprinkler system, we're going to have the most restrictive criteria in the building code applied. You can see that exit corridors, okay, again, this is a way that occupants ultimately get to an exit stairway. We have our own flame spread criteria. Again, it's consistent with the building code. Class B in non-sprinklered, and then Class C in sprinklered conditions. And then when it says rooms, that pretty much is what is called exit access. Now, exit corridors are actually a part of the exit access, but these are the rooms in which we all work, we all play. We're all, using some service or, perhaps living in some cases, not with this particular table, because this one applies to offices and to stores. But you have people that are taking advantage of whatever service, whatever product is being shown there or used there. So we have travel distance limitations in these rooms, and we want to make sure they get to a place of safety as quickly as possible. That is built into the FDS. We're not trying to get out in front of the building code to provide any changes to that or the way we think about the protection of occupancies. We want to work hand in hand with the building code in these particular cases. So we're just going to take a little bit of a jump. We're not ending the the presentation here. The supplement in the FDS itself actually has a flame spread performance of all kinds of wood products and the like. You can see the same table at the bottom left-hand side of your slide and the like, but it's consistent with a document that has been published and is supported by, obviously, the American Wood Council, and it's called Design for Code Acceptance, or what people call DCA. Okay, the DCAs themselves are intended to provide a lot more guidance than building codes and other types of documents can provide. Okay, this one is DCA 1. It was developed prior to the creation of the FDS, but all of its materials are intended to be, or have been, incorporated into this particular supplement. So we have then more information that had been developed from the past by AWC engineers built into this fire design specification. Very, very nice to have all that handy in one document. So we're still staying in chapter 2. Okay, the vertical and lateral flame propagation and whatnot. We've tested that. We know, certainly you can see the picture of the high rise on the left-hand side. It's fairly small, but you can see that if this is not taken care of, flame can propagate, certainly vertically, very quickly up exterior walls even. And so we have a lot of that criteria. The reference standard that is used in certainly most cases, if not all cases, is NFPA 285. That is referred to here. It's also proven useful in promoting fire retardant treated wood as an exterior covering in certain applications, which is nice as well. You can see that in the second bullet too. So we're building in some of the more recent concerns with fire propagating, certainly vertically in high-rise conditions. We have a lot of protection features and systems in these high rises, but if they go on the outside of the building, they are not being suppressed by the fire sprinkler system at that point. And so we want to make sure that we're protecting the occupants by limiting its ability to move vertically and even laterally too, certainly in these kinds of situations. As I said before, we're 2.5 in the standard itself deals with fire stopping, fire blocking, and draft stopping. We've had that for many, many years. Certainly the fire stopping criteria, which really was started by the nuclear industry in terms of providing protection for their particular facilities and all of that, brought that ultimately, the industry, 3M, some of the other types of industry groups, brought that to the building code process and got it included within the building code itself. So we have membrane penetration criteria, through penetration criteria, and then again, as we mentioned, very, very concerned about the protection of joints and that kind of a thing. We have products like that. There are a number of products that can be used. You look for listed, if you will, types of products out in the field. Hopefully from a design standpoint, you can go and find these products fairly easily online, I would expect, and then apply them appropriately as a result. And a lot of the material instructions that are provided by the manufacturers do talk about the proper use of their products too, and they are very, very concerned too with protecting the occupants within the built environment. Now, as mentioned before, fire blocking and draft stopping, that's been in the wood chapter of the building code for many, many years. Obviously, if fire happens to gain the inside, if you will, or the interior of a wall assembly, things along those lines, some kind of a vertical assembly, then we're going to have fire blocking applied. Many of the prescriptive criteria that we're used to are listed in the FDS as well as in the building code. So we have that too. It's coordinated there. Draft stopping obviously is typically applied to horizontal assemblies, to attics, perhaps to floor ceiling assemblies, and just to cut down on the areas to, like with fire blocking, to restrict the passage of the flame front in particular in these large open concealed areas. So they have 6 different prescriptive materials that are applied there. We're all very familiar with this. and have been doing this for many, many years. So it's in the FDS, and it's coordinated with what's in the building codes as well. Okay, moving on to Chapter 3. Chapter 3 really establishes the fire resistance design provisions that apply to all of these wood members, assemblies, and as I said, you can see Section 310 connections as well that use the NDS for design. Okay, for those of you that are familiar with the 22 edition of the FDS, the format of this chapter has changed slightly, just corresponding with changes that are in the 2024 edition of the National Design Specification itself in Chapter 16. So again, there's a coordination effort that occurs even within between standards and the building code itself. So again, like all chapters, we have a general statement. Then we get into different types of elements. We talk about the charring of wood. We talk about how you certainly can determine that. We talk about in Section 3.3 the structural fire resistance of exposed wood members. Okay, these are solid members that we can, beams and columns that are just wood. And so there's no interior, if you will, concealed area within them. We're protecting the wood members so that structurally they will be able to withstand certainly the fire for the time that it is, if you will, you're calculating. Okay, we talk about assemblies. Okay, wood assemblies. Okay, and protection of members too, but we're starting to get into the assemblies themselves. In 3.5, then we get into the structural fire resistance of those wood members and assemblies. Okay, the calculation method, I should say. Then in 3.6, we're going to talk about certainly thermal separation time. And then 3.7, the calculation of burn through time itself. Sorry about that. Stumbling over my words a bit. So moving on along, when we get to 3.8, obviously, if you have assemblies, if you have protection that has already gone through the ASTM E119 fire resistance test or the UL 263 fire resistance test, that's addressed in there. Okay, and then at the end of today's presentation, we're going to talk about the component additive method. Okay, we've actually had this for a number of years in various ways, scattered around in various codes, showing up in perhaps existing building codes or, that kind of a thing, so that we can actually look at, in the past, certainly existing assemblies and try to make sense out of them from a fire resistance standpoint. Well, now we have this for the new construction too. And then, as I mentioned before, one of the more interesting things to me is how we can calculate and then design and install the wood as being the protective element for connections. Very, very interesting to see that to me, because that's in some ways the newest criteria that we have in this particular standard for lots of us in the business. So Section 3.2, as you can see here, we determined the actual char depth, okay, in Section 3.2.2. You can see in solid wood, we have equations, and in CLT, we have basically a summation of the layers, if you will, the char within those layers too. Now, I know that a lot of the jurisdictions that are in the United States do not have necessarily the expertise or the capability. This is a new standard. Not many people have the expertise or the capability to deal with this yet. So I would expect that, and frankly, if I were the building official of those jurisdictions, I would expect that I am going to get an engineered type of analysis from probably a fire protection engineer, but that's not necessarily the case. Could be a civil engineer, could be, in some states, a registered architect that has experience in this. But whoever is doing this needs to have experience with this, needs to have a good knowledge of the criteria in this particular standard to provide this to the local jurisdiction. And then once the jurisdiction gets it, there's a number of ways of handling that. Obviously, and again, in some of the larger jurisdictions, you probably have people that are going to have at least a familiarity with this kind of criteria. But if you don't, you might even ask for a peer review. You might even see if there is an engineer or somebody out there that has experience with this criteria that on behalf of the local jurisdiction can review it and determine whether or not what they say is accurate, and then ultimately it's equivalent to what we're looking for in the building code itself. Okay. The two bottom, and actually I guess technically the three bottom graphics, there's one picture, but the graphic on the left really shows a beam and what happens in the event of a fire, at least certainly what is being considered in the design of the beam, okay, in the event of a fire. Now, not every fire is going to provide an equal char layer level on all exposed sides, but that's how this particular standard works because we have to be conservative, right? And so what ends up happening, and the analysis that really comes in, is that when a structural engineer or someone who is designing the structural system is looking at this particular building and having exposed beams that the beams themselves are providing the protection, you actually, and it's not the right term, but it's the only term I can come up with, oversize the beam to basically accommodate the char layer so that the size, the structural design size of that, in this case, wood beam, is actually protected by that char layer itself. So you're going to see larger wood elements in these particular cases. And when you get, if you move over to the right-hand side, you get intersections, you get other types of members where you're actually combining elements. Then you have an analysis of where that intersection or that joint is. And you can see that fire does have, on unprotected exposed joints, does have a little different effect there based on this analysis. So this is where, you know, we're going to need a lot more training. Certainly, I'm hoping to provide more training to our local chapters, to our local building officials, and those other people that have an interest certainly in this, so that they can analyze these exposed wood elements against the requirement for a certain amount of fire resistance. So it makes it very, very interesting to see this type of analysis and to actually see in the built environment the use then of wood to provide fire resistance protection. So here we are. We have some fairly detailed, obviously, criteria related to char depth, what we're looking for, what we're assuming, certainly for various elements. Okay, you can see table 3312 there provides you with the depth and the effective char depth based on certainly a required fire resistance rating for that particular element. The new product is found in the lower table, table 3313, which really is intending to address CLT. This gets to our mass timber design criteria and will allow us to analyze the fire resistance design criteria that is in the code against, you know, what we can design for in these particular members and elements. And so you can see the char depth and the effective char depth for CLT based again on what is being required from a fire resistance standpoint. Okay. Another aspect of this is if you design a certain sized wood beam, then if that beam is in an exposed manner is providing fire resistance, we may have, and we do have, adjustments to the strength design of those beams. So again, the structural capacity of that element is provided even during the fire for the time period, 1 hour, 1.5 hours, or 2 hours, that's being required for that system by the building code. So very, very interesting to see this. There are programs out there, educational programs. There's a technical certificate program through Cal Poly San Luis Obispo, Cal Poly, University of Maryland, I think Worcester Polytech. It could be also Oklahoma State. I haven't checked there, but they have some good fire protection engineering programs there that have, if you will, a course, or at least an element within a course that talks about how you design exposed wood members, exposed elements for fire resistance design. So very, very interesting to go through that and know that there are resources out there that you can use if you wish to really dive into this more deeply. Here we get into our assemblies, okay, and we start to talk about again, the protection that is provided by the membranes that are protecting the floor ceiling and maybe even roof ceiling assemblies, things like that. We know that wood structural panel, plywood, particle board, things along those lines can be used in these ways. So we have a wood cover criteria. You can see the equation there and the time that ultimately is developed. You can see that we could have other types of membranes, such as 5/8 type X or whatever, gypsum panels, and then we have criteria for that as well. Okay, that's all built into this particular set of criteria. Very, very interesting. It really combines into one standard pretty much all of the fire resistance types of issues that we have with wood construction in particular into one place. Very, very nice to have that. Now, when we get that the time period, excuse me, attributed for those elements or those particular products and things of that nature, we actually go through and we combine them. We add them all up together, and that gives us, if we have like a floor ceiling assembly, that gives us the rating of that floor ceiling assembly. Or if you have a beam or a column, typically it's just one layer, a 5/8 type X or whatever, we get that T sub P, and that becomes the rating of that particular assembly at that point. Very, very interesting to see that. This is really the thermal separation in this particular case. The previous slide was the structural fire resistance. The thermal separation, whoops, I didn't get to that slide. There we go. The thermal separation criteria found in section 3.6 really does intend to cause us to be more comfortable with that assembly that's being provided in terms of what temperature rise might occur on the unexposed side. So if you have a floor ceiling assembly, obviously we test it from the bottom. It's the most conservative way to test horizontal assemblies. And then we measure, when we go through and test them, we measure the heat rise on the unexposed side. This gets us to that point. And so when we go through all of that and we get to that top, if you will, membrane, whether it's wood structural panel or it's 5/8 type X, we have a T sub P that is actually provided, but we actually pull back on that criteria a little bit. So with wood, it's 85% of that time that's attributed by calculation method, or with type X gypsum panel, it's half, it's 50%. And then what's really, really interesting to me, and granted, I've seen this over the years, but there is actually a very nominal amount of time, if you will, fire resistance, in this case, thermal separation time, attributed to the presence of insulation. It actually does serve. It's been shown through the research that has been done. Okay, it actually serves to contribute to the resistance of the rise in thermal separation of a various assembly. So we account for that in this particular section as well. So then burn through time. This is a very interesting one. It really is only required where there's thermal separation requirements. So we have the different requirements. When you have a beam or a column itself, we're concerned about the structural fire resistance of that element, that beam or column. When we've got an assembly, we're concerned about the structural fire resistance, but we're also concerned, like I said before in the previous slide, with the temperature rise on the unexposed side, thermal separation, and we're concerned about the potential for fire to leapfrog or to pass through an assembly. That is the burn through time. And so we have all of that criteria in this section as well, in section 3.7. Very, very interesting to go through all this. These three sections themselves, 3.5, 3.6, and 3.7, are really something that is an expansion of what we've done in the past. We really, again, only looked at the criteria, at least in my mindset and in the enforcement side. We really only looked at the criteria for structural fire resistance, and the thermal separation time was actually built into the test standard itself, as well as the burn through time. Well, we have that now prescribed in the fire, if you will, fire design specification. Okay, it's here in front of us now. So you don't actually have to go through, if you will, and look at in great detail ASTM E119 and then certainly the results of the tests based on that standard to decide what, or to determine what those times are. We're going to have that here. So then, as I said, we always have the ability to look at those products that are tested in the furnace, either through ASTM E119 or UL 263. You can see examples of this here. Industry has done that. A lot of that criteria in more detail is found in the supplement B of this standard itself, which is this next slide. So you can see right here that we have another DCA, Design for Code Acceptance, number 3. This has been used a lot, actually, in Type 3 construction. People are starting to look at this for wall and floor ceiling assemblies. Okay. Very, very handy to have this. It's built into the FDS now. Okay. We will have this available to us to use in one document. Okay. We don't have to have, you know, a number of different documents all in one book, if you will. For some of us who like hard copies, it's a real book. Otherwise, you can go on the AWC website and see the electronic version itself. Okay, it's provided for you free of charge. So then moving on along in chapter 3, I talked about the component additive method. We have different methodologies to look at, certainly the combining of various elements to create the fire resistance of assembly or protection we're looking for. So you can see there's some examples here. We have from the structural fire resistance. Okay, we have 2 elements that are provided. For one, the 5/8 type X, only on the exposed side is provided. That's at the bottom of this listing there under structural. And then the 2x4 cavity that has insulation, in this case, 3.5 inches of mineral wool. It says mineral wood. It should be mineral wool, I think, in this particular. I didn't notice that until just now. That actually makes up the fire resistance rating of this assembly. And so you can see that we get 40 minutes for the single layer of 5/8 type X. That'll be consistent through all these slides. Okay, and then for the 2x4, if you will, package with the mineral wool insulation, 23 minutes together, added together, that is. They make up 63 minutes. Obviously, that is more than enough for a 1-hour rated assembly. Then we have a thermal separation condition, okay? And as I showed you in the equation, there is a reduction for that on the unexposed side for that membrane. In this case, it's 5/8 type X. I said it was a 50% reduction. You can see that in what we have here is the 40 minutes times obviously 50% is 20 minutes. Then for thermal separation, the 2x4 studs with the insulation, it makes up 19 minutes. Obviously, the 5/8 type X on the exposed side is 40 minutes. Altogether, that equates to 79 minutes. That still is more than enough for a 1-hour rated assembly. Okay, very, very interesting to go through this. As I said before, we've had other older codes that have had this kind of method built in. They just didn't have it to this degree, and certainly it wasn't nearly as clear as it needed to be to use it. Now, when we have other types of assemblies, okay, we have other types of methods we go through. In this case, it's regular 2x elements, 2x10 joists that are protected on the exposed side, the lower side, 5/8 type X, and then on the unexposed side, the floor side, 1/2 inch wood structural panel. Okay, so from a structural fire resistance standpoint, the code, the standard actually gives us 27 minutes. 5/8 type X, as said before, always 40 minutes, right? So 40 plus 27, 67. That is exactly the same. Okay, thermal separation, we go through, obviously the 5/8 type X is what it is. The 2x10 joisted assembly with the mineral wool and whatnot, 15 minutes. And then we have the reduction for thermal separation for that membrane on the unexposed side. Okay, so wood structural, 1/2 inch wood structural panel is given 14 minutes as a general rule. And then we take 85% of that. All of that, go figure, somehow comes out to exactly the same combined assembly time, 67 minutes. So if we go back to the previous slide, you will see that in red at the bottom for the combined assembly time, we have 63 minutes, but the thermal separation is 79 minutes. The assigned fire resistance rating then is the least amount of the combined assembly time. So in this particular case, this additive method, they came up with exactly the same. So 67-minute assembly, it works for 1 hour fire resistance rating itself. Now, we have another consideration, the burn through. And the burn through for this, and we just didn't have the information on this, without the additional floor cover, comes through at 62 minutes. So technically it should be 62 minutes. Again, it's still more than enough for a 1 hour fire resistance rating. Now, the last one that we have here for the component additive method is an assembly that uses engineered I-joists, wood I-joists, to be specific. Okay, so we have two actual structural fire resistance determinations that have to be conducted, and then the thermal separation, and of course then the burn through. So we go through, we look at the flange itself of the I-joist assembly. Okay, and again, 5/8 type X is noted, it's always 40 minutes. The wood I-joist assembly in the information found in the back of in the supplement and all that, with the mineral wool and all that, and it's spelled correctly there, that's good. Comes out with a 26-minute fire resistance rating. Obviously, we add those together, 66 minutes. Now we have to consider the web, because the web it's not a different material exactly, but it's a different element altogether than the flanges. So we go through that, 40 minutes for the 5/8 type X, and then the web of the I-joist is given 20 minutes. That's exactly 60 minutes. Okay, that's right on the button, right? So we have another determination. We go through the thermal separation analysis or method. And again, what you see there, because we're using wood structural panel on the unexposed side, we get 85% of the value for that 30 seconds wood structural panel, which is 13 minutes. So all that together is 66 minutes. The burn through calculation itself is estimated at 61 minutes. So the assigned fire resistance rating for this particular assembly is 1 hour, 60 minutes. Go figure, we created the examples to come out exactly like that, right? So it's very interesting to go through these component additive methods and to look at these various assemblies that are out there against the testing information, the research that's been done and really provided for in the FDS itself. Very, very interesting. So then we move to the next section. And this, like I said, is perhaps my area that I find the most interesting, because I did not anticipate to see exposed wood members providing protection for various types of connections. Okay, you can see in the upper left-hand corner, we have, presumably, it looks to me like CLT assemblies. And then we have a floor assembly with a wall assembly. There's a metal connection that is, bringing the two together. And then you can see in the dash lines itself, the designed connection. Okay, it's made up of three. It just blows my mind every time I look at this. I believe it's three wood, 2x wood elements. Okay, and then there's a little bit of a 2x blocking that is providing support for that to cut off, if you will, provide a little extra, if you will, protection for the joint that's formed between the connection members and, in this particular case, the wall assembly that is being provided. So you can see the analysis from the char standpoint that occurs, and you can see that the wood members actually in that particular connection do serve to protect the connection throughout certainly the expected life or the expected fire resistance time in this particular case. Okay, very, very interesting to see that. Again, like I said, I did not anticipate this coming into the fire design specification when I first heard of it. And I find it, again, to be something that might be one of the biggest changes that we have to deal with, certainly from a design plan review, and most definitely for our inspectors out in the field, because, people are just not used to seeing that. Okay, you can see that there are other types of connections that are built into it. If you go just across in the right-hand side there on the upper part of the slide, you can see a plan review of a beam to perhaps a column or to a wall or what have you, and the char analysis that occurs there, okay? And then the char analysis that occurs that maybe when you're strapping across a couple of different elements itself, okay? This is basically the FDS as an overview. We have a number of different standards that the American Wood Council maintains and publishes and makes available. You can see the FDS located there. Most of the standards have been updated to the 2024 edition. It is a family of wood design standards. Obviously, the patriarch, I think, is the National Design Specification. Some people might argue with me on that, but that really is our structural design standard that we have used for many, many years. AWC is going to continue to do its research, continue to do the studies that are needed to provide the protection that's necessary, and then continue to push for adoption and reference of these particular standards in the various model codes, even perhaps legislation out there, although we're not big fans of having building code criteria in legislation, but to make sure that we get the latest and greatest out there in the hands of the people that need it. Okay, and frankly, a lot of our engineers and our architects are held to higher standards from a liability point anyway. And so when industry of whatever type produces new standards, new criteria, they're going to have to understand this and look at this in their designs. And certainly the NDS they get, but the FDS can be used, certainly starting in the 2024 edition of the building code. It can be used now as an alternate, however. So very, very handy to have that. As I mentioned before, AWC continues to support and conduct all kinds of research. You can see that we're looking at, based on our mass timber criteria, looking at increasing the amount of exposed wood in tall wood buildings. We're looking at all kinds of new stud wall and floor ceiling assemblies that are being out there. People are very, very creative, and they come up with all kinds of different ways of creating the assemblies that we need in the built environment. There's new investigation of combined moisture and thermal influences that are occurring, and then certainly new protection designs, again, with people who are so very creative out there. There's been so much progress that has been made really in the last 35 years, which in a lot of ways is very, very recent. This kind of progress really is only possible by supported research by industry and by others that are out there that really lead us to these, frankly, design breakthroughs. Okay. We do see an increased need for more research, like always. The Forest Products Lab is doing all kinds of work, and many others. We're very excited about that moving on into the future. So with that, I want to thank you. This is my name, obviously Paul Armstrong. I'm the Western Regional Manager of AWC. It does not have my email address, which is parmstrong@awc.org. Feel free to use that anytime. I really like to get to know people across the country, but also to know the concerns and issues that you might have in your areas. With that, Annie, I'm going to turn it back over to you for any questions that there might be. Take care, everybody.